right, this one is a multi-step problem. We have steps A through D. So this is going to bring in everything you could possibly calculate in stoichiometry. I'm going to start by copying my equation down below, and then I'm going to write my chart, grams, molar mass, draw a line, moles, coefficient, draw a line, and then equivalent. Okay, so I'm going to read what they give me in the problem, and we're going to notice they give us two things this time. If I do this reaction with 35 grams of C6H10 and 45 grams of oxygen, this, because you have two givens, means this is called a limiting reactant problem. This means that one of these two is going to limit how much we can make of the products, and the other is going to be in what's called excess. So the last of it is how many grams of carbon dioxide are going to be formed. So I have to figure out which one of these two is going to be called the limiter and which one is going to be called the excess. So we're going to do this problem the same. We're going to find the molar masses. I'm going to find it for this, this, and this. So from the periodic table, we get 82.16 here, 32 here, 44 here. Now I'm going to divide these two by their respective molar masses to get the amount in moles. So this gets me 0.426 moles, and this gets me 1.406 moles. Now I need the coefficients from the equation. This is a 2, this is a 17, and I'll divide these by their coefficients to get the equivalent. Now this is important to note. We have two different equivalents here, but only one can be the true equivalent, and it's always going to be the smaller of the two. This is the smaller of the two values, which makes this a worthless number. This is the true equivalent, which is going to be the equivalent of everybody in this reaction. That means this has the title of limiter, and this has the title of excess reactants. That's the limiting reactant and the excess reactant. Because this had the smaller equivalent, it is the limiting reactant. Because this one had the larger equivalent, it is in excess. And then this number, again, is meaningless. This is the true equivalent, which means that this number here is also a worthless number. So I'd actually cross both of these out, and then this is the number you would have to use instead. Okay, so now the question is, how many grams of carbon dioxide are we going to make? And I rewrote the equivalent in all four spots here. And so now we're just going to work our way up from here to the grams of carbon dioxide. So I'm going to multiply this times the coefficient of 12, which gets me 0.9924 moles, and then multiply that times the molar mass, which is 44, and we get a value of 43.67 grams of carbon dioxide produced. Everything is based off of the limiter in any reaction, because once you run out of the limiter, that's it. Your reaction can only go as far as the least amount of reactant that you have available. So now there's one more step we're going to do, and that's going to be, two more steps. Next, we're going to figure out how much excess is there. We have 35 grams to begin with, but how much of that am I going to have left over after this reaction? In other words, how much of this 35 grams am I going to use up? So I'm going to put a little subtraction sign here, because what I need to know is how much my amount consumed of C6H10. And so to figure that out, I'm going to use this 0.0827, multiply it times the coefficient, and I'm going to get the true amount of moles, 0.1654, and that's how many moles we consume. But I'm going to go ahead and convert that to grams by multiplying it times the molar mass up here, and then I can write the amount consumed is 13.59 grams. So I started with 35 and I consumed 13.59. So how much of the 35 do we have left over? And when you subtract the two values, we have a total of 21.41 grams of excess that remains. And so that's the third thing that we figured out in this problem. This is how much theoretical yield of carbon dioxide we've made, and this is how much excess C6H10 we have left over after this reaction has gone to completion. Okay, so if we look up above, letter B said, what is the limiting reagent? And we determined that the oxygen was the limiting reagent in this problem. how much excess reagent is left over, and we determined that there's going to be 21.41 grams of C6H10 remaining or in excess after this reaction is completed. Remember, we started with 35 grams. This is how much is left over of the 35. All right, and last but not least, it says that if 35 grams of carbon dioxide is actually formed, so this is an actual yield, which means we want to use the equation actual over theoretical times 100. Actual yield divided by theoretical yield times 100 gives us a percent yield. So in this case, the actual yield is 35 grams of CO2 divided by the theoretical yield is 43.67 grams of CO2, times that by 100, and we get a percentage of 80.15%. And that is the answer to letter D. So here's one final practice problem. Attempt it on your own. Pause the video now, give it a try, and then you can unpause the video to watch the solution. So I rewrote the equation below. I wrote my little chart on the left-hand side. Now we're going to identify our givens. We have two givens, 150 grams of the lead sulfate and 600 grams of the lithium nitrate. How many grams of lithium sulfate will be formed? So I've rewritten that down here, and because we have two givens, this is a limiting reactant problem. I have to know which one of these is the limiter and which one is going to be in excess. But first, we're going to go ahead and add up the molar masses of all three of these, which should be 399.34 grams per mole of this, 68.95 grams per mole of that, and 109.95 grams per mole of this. Now, I'm going to divide this number by this number to get the moles, and this number by this number to get the moles. That's going to get us 0.3756 moles of this and 8.702 grams per mole of this. I'm going to put the coefficient, which is a 1 here and a 4 here, and now I'm going to divide these in order to get the equivalents and compare them. So we get 0.3756 versus 2.175. That means that this is the true equivalent, which means this is my limiting reactant, which makes this the excess reactant. And notice, because this is the excess, that number is worthless and that number is worthless. I have to redo those numbers. So this is the equivalent. I'm going to rewrite it across for everybody. Now we're going to multiply our way up in order to determine the amount of lithium sulfate produced. So the coefficient here is 2. Multiply the equivalent times the coefficient to get the moles, 0.7512, and then multiply the moles times the molar mass to get the grams of lithium sulfate produced, which is 82.59 grams. This is a theoretical yield of lithium sulfate produced. Okay, now the other question, or letter C, says determine the amount of excess formed. So I'm going to use my equivalent, multiply that times 4 to get the new moles, which is going to be 1.502, multiply that times the molar mass, and it's going to be 600 grams minus, and this number that we're getting is the amount consumed. And that number is, when you do 1.502 times 68.95, you get 103.59. That's how much we consume of the 600. So when I subtract them, then I'm going to have my amount remaining, which is 496.4 grams of excess lithium nitrate. Letter D says if the reaction is only 87% efficient, what is the actual yield? So remember, we use actual over theoretical times 100 to determine the percentage. But this time we're told the percentage is 87, and the question is, what is the actual if the theoretical is 82.59? So you're just doing some algebra here to solve for the actual yield, which is going to be 71.85 grams of the lithium sulfate. So we just took 87% of this theoretical yield to get the actual yield. So up above, we're just going to make sure we answered all of the questions. We figured out how much lithium sulfate would be formed. That's 82.59 grams. The limiting reactant was the lead sulfate. How much excess reagent was left over was this 496.4 grams of excess lithium nitrate. And if the reaction is 87% efficient, the actual yield is 71.85 grams of lithium sulfate. And this is absolutely every single possible question you could be asked about a stoichiometry problem.